So the discrete dislocation stuff is there. I'll do a little more multiscale thing here, and then maybe we'll come back to the discrete dislocations. A number of the things that were in the discrete dislocation lectures, I'll just mention, come from some of the work that my colleague Alan Needleman and his co-workers, Eric Vandergeest and Vikram Deshpande, have done. I didn't write all the references in there, so a lot of the figures that are in lecture 4 come from the Vandergeest and Needleman works mostly on fatigue. And the goal there was to show you some of the things that are really fairly subtle that come out in doing fatigue modeling. But maybe we'll come back to that. What I'll do now is talk about coupling a couple of things, give you an idea of what one has to do if you want to try to couple methods. And then it'll be some parts. So we're already have shown you this before, and we're really trying to think about what goes on at the atomistic scale, but we want to be coupling to the dislocation scale because we're not just interested in the crack tip, we're interested in what goes on sort of in the interaction between the crack and the dislocation plasticity that goes on around it. So the general goal is to try to do two things at once, as I showed you a cartoon before, and it's to have a material where the crack tip region is fully atomistic, molecular dynamics, and in there that means we can have whatever happens at the crack tip, including dislocation, nucleation, chemistry, maybe grain boundaries, other messy phenomena. That means you can't always predict what's going to happen under very high stresses near a crack tip. And so could have interfaces, could have boundaries. But we don't want to have any restrictions. That is, we want that region to be molecular dynamics, whatever molecular dynamics gives us. And outside of that, at some larger scale, we're going to have discrete dislocation plasticity, where the only thing that can happen is dislocations can move back and forth through the material, give us plastic strain due to dislocations. So this is very important, the plastic behavior out here. All of the non-dislocation plasticity stuff is confined to some region here in the atomistics. So we think about this in terms of retaining the atomic scale detail where we need it, where we think things could happen that we can't describe at the higher scale. And at the higher scale, we will then have the important part, the part that's giving us the toughening, that's determining what the conditions are at the crack tip, which is the dislocation plasticity. Let me, this is almost a hand-drawn picture because I drew this picture back before we'd actually ever developed the method. So it was not a very good advertising, but the one thing about having this kind of method is that you want to have these two regimes, these two different domains, talking to one another as perfectly as possible. And there are two things that have to be done perfectly. One is that the stresses and deformation in here have to be transmitted out here, and the stresses and deformation here have to be properly transmitted here. That is, the mechanical coupling at this boundary has to be precise. We can't introduce errors in that coupling because errors will then move the dislocations in the wrong positions, and if the dislocations are in the wrong positions, then the crack will see the dislocations in the wrong positions, and the crack will do the wrong thing. Dislocation fields are very long range, particularly in 2 dimensions, but in general going like 1 over distance. And so if you do something wrong over here, that effect percolates over long distances. So you have to be very careful about the coupling, just mechanical coupling between atoms and continuum. The other aspect is that the dislocations are not confined here. They can exist here, and they should be able to pass back and forth But if I have a dislocation out here and it wants, the field is driving it into this material, it should be able to enter that material. And if I have a dislocation, say, nucleated by the crack, it should be able to go out into the continuum, and there shouldn't be any inhibition at the boundary. The dislocations shouldn't know that the boundary is there, okay? And if the dislocations know the boundary is there, then this is a numerical artifact. So those are the two things that we have to worry about. And so this method that we developed, we called CAD. It's not computer-aided design. It's coupled atomistic discrete dislocations, got an extra D. And we have a basic problem of one domain, which is a linear elastic material with dislocations, discrete continuum dislocations. So the plasticity comes from the motion of dislocations. The surrounding underlying material is linear elastic. That is, the atoms are under small deformation. They behave linearly, so we don't have to worry about the atoms. And then in another domain, we have a fully atomistic crystal, and I can have defects in there. And then I have an interface, and it's permeable to dislocations. That is, I have a way for the dislocations to go back and forth. And then this is a general boundary value problem where I specified tractions and displacements, and I want to solve this problem. And this is another one of these problems where we're, at the moment, limited to plane strain. What that means, we're limited in plane strain for dislocations going across the boundary. So these dislocations are line defects that are always coming out of you, out of the plane, and we're looking at a plane strain problem. We're now working on full 3D implementations of this where the dislocations are loops that can be in the continuum and go into the atoms and come out somewhere else. That's rather difficult, and it's still work in progress. So what you see is what you get here. It's a two-dimensional plane strain. Dislocations are either here or here, but they should be able to go back and forth. So how do we deal with this? Well, there's a lot of different methods for coupling atoms and continuum. As a matter of fact, there are approaching 14 or 19 different methods. And why there are so many is a good question. There don't need to be so many, but they are. So there's a review article a few years ago that actually did the nice work of comparing all the different methods within one code and for a couple of non-trivial problems, and showed that most of the methods, that the earlier methods worked the best and were the most computationally efficient, and the later methods all worked worse and were more computationally expensive. But people like to develop their own methods. So this is one of the early methods, and it's more or less flawless. So we take the full problem, and we kind of do the obvious if you're a computational person. You do something like domain decomposition. You say, I have two problems. I have a discrete dislocation problem, that is, I have a continuum material with dislocations, and I have a fully atomistic, a fully molecular statics. We won't worry about dynamics, we'll just talk about molecular statics. So atoms move to forces equal to 0. A fully molecular problem. But the two problems are coupled through some sort of displacements and forces at the boundary that they share, okay? And somehow we're going to consistently make sure that the displacements are the same and that the tractions, if necessary, are identical. It's a little bit subtle about tractions. I'll come back to that. But we're going to solve one problem, and this is just a discrete dislocation problem, and all continuum with the discrete dislocations. This is an atomistic problem. Now, discrete dislocations itself we solve by decomposing that problem into two pieces. And this is where elasticity is important. So this is a problem with an elastic medium with these elastic defects. That is, the dislocations generate strains, and I have to deal with all the boundary conditions, but everything is elastic. So these problems are solved using a superposition method. The superposition method takes the dislocations in an infinite space. So this is a fictitious boundary in this problem. I just sketched it in with a dashed line. dislocations in infinite space, we know the solution for a single dislocation field. So we can look it up. It's analytic fields. Okay? If I have multiple dislocations, we have elasticity. So we can just sum up the fields of multiple dislocations because of superposition. This elasticity, right? It's a linear problem. So if I have dislocations in an infinite space, I know the analytic solution for the stress and displacement fields everywhere in the material, in the infinite space. Now, if I look at the actual material of interest, the stresses caused by these dislocations in the infinite space gives me some traction T tilde and some displacement U tilde. Those are not the traction and displacement of the original problem. Okay? So this alone, just drawing the dash boundary, doesn't satisfy this boundary value problem. I have to do a separate problem to correct for these fields on the boundary, and that problem is on the physical domain, and there are no dislocations in that problem, but the boundary conditions are my actual boundary condition minus the traction here for the traction boundary, and the actual boundary condition here minus this displacement here. And this is now just a continuum problem with specified boundary conditions, no dislocations at all. And if I take this problem with the dislocation fields and these boundary conditions, and I add it to this problem with no dislocations and these boundary conditions, then you can see when I add them together, this is a linear problem, this is a linear problem. When I add them together, the T tilde and the minus T tilde cancel out, and I get the T0. The U tilde and minus U tilde and plus U tilde cancel out, and I get the boundary conditions of the real problem. I can do this because of superposition. So these two are linear problems, and so I can add the solutions together. The solution of this boundary value problem satisfies equilibrium. I do it with finite elements, right? It satisfies divergence of the stress is 0. The solution of infinite dislocations in an infinite medium satisfies divergence of the stress is equal to 0. When I sum the two together, divergence of the total stress is 0. So I've satisfied, as long as I satisfy the boundary conditions of the full problem by superposition, I satisfy the full problem. So this is the core of the dislocation dynamics methods in general, that we deal with this complicated boundary problem with the dislocations giving long-range fields by dividing it into these two pieces. Okay? So I go at length here because I probably won't do the discrete dislocations, which was the previous lecture. So this is just discrete dislocation method. And this is the beauty of elasticity. The plasticity is the motion of these dislocations. But at any instant where the dislocation positions are fixed, I have an elasticity problem. And elasticity problems are easy to solve numerically. Okay. So this problem is decomposed into two problems, but I won't come back to that. I'll go back, and now we know how to solve this problem specifying the boundary conditions, and this is an atomistic problem. So the trick is that when I do this and I cut these into two pieces, if you're a continuum mechanics person, you say, yes, I can take any body, I can cut a slice through it, and I can apply tractions on the boundary to keep the boundary in the cut position. I create a free body diagram. We do this all the time in mechanics because everything in mechanics is local. I cut the body, apply tractions, I have a free body diagram, it's perfect. You can't do that with atoms. Okay? If the interatomic forces in atoms are non-local. So what does that mean? Here are atoms. What that means is that this atom actually interacts with this atom over here. Right? This atom interacts with that atom over there. This atom interacts with that atom and this atom. Right? There's a region around any given atom that influences what goes on in that atom. It's not just near neighbors. It's not just this atom interacting with its near neighbors. It's interacting with the whole domain. So it's intrinsically non-local. So let me see if I have a better picture. No, I don't have a better picture here. So look over here. If I cut an atomistic system and I make an interface, so this, think of it over here as a free boundary. These atoms, and I want to, in continuum mechanics, I would just say, look, I just have to apply forces to these atoms on the surface, and then I'll have my free body. I'll have this body with the forces applied. But in fact, these atoms in here are missing atoms that used to exist over here. And so these atoms should also have forces on them if I wanted to really reproduce exactly this structure. That is, there's a kind of a domain over which the system is non-local. I can't just cut and apply forces. So what that means when I go to coupling between an atomistic system and a continuum system is the atoms, which terminate here, these are the real atoms all inside here, and these are the interface atoms. These atoms have to see other atoms that are lying formally in the continuum domain. So what we have is an atomistic system, but we have some extra atoms. And those extra atoms, the purpose of those is so that all the atoms in here see all the atoms they really should see if it were an infinite atomistic material. And we call these pad atoms because they overlap. They're a pad that overlaps with the FEM nodes or the FEM displacements, but they convey information, they convey forces, fully non-local forces from these atoms into the interior. So these atoms do not know that I've made a transition to finite elements over here. And what happens is these pad atoms, their positions are controlled by the finite elements. Okay? So I have these atoms in the system, but I tell them where to go based on the solution of the finite element problem. Finite element problem gives me displacements. I use the interpolation of the finite element fields to tell me exactly where these atoms should be. I then put those atoms in, and those atoms then exactly transfer all the correct forces to the real atoms in the system. So these real atoms, the only thing they know, the only reason they know FEM is here is because these atom positions are controlled by FEM. And if the atom positions are exactly correct, these atoms don't even know that FEM is controlling things over here. So I have an atomistic problem which terminates with the black atoms here, and then I have these pad atoms on the outside that transmit the FE deformations to the inside. The FE problem is local. All the FE problem needs to know is what are the displacements on the boundary. Right? The FE, if this is a node, it doesn't care what this node is doing. All it cares is what's going on in the elements around me. FE is completely local. Right? This node only depends on the nodes around it. It doesn't care what's going on over here. So having the atoms talk to the continuum, all we have to do is tell the continuum where the boundary is, and that's the black atoms. Having the continuum talk to the atoms, we have to have the continuum say, hey, if there were atoms here, this is where they would be, and now these atoms will talk to these atoms over here and tell these atoms what to do. So there's an asymmetry in how the FE talks to the atoms and the atoms talk to the FE. Okay? And if you don't get this right, then you introduce all kinds of errors at this interface. So if you think about algorithmically, what we do is you think about fixing the atoms on the interface. Then the finite element problem is perfectly well defined because all the boundaries are specified, and we find the continuum positions of all the nodes in the finite element. Then we find the positions of the atoms in this pad region by interpolating from the positions of the finite element nodes. And then we take those pad atoms and we put them in the atomistic calculation at exactly these positions. And then we let all the atoms in the system, except for these guys, we let all those atoms respond. And so we move those real atoms. And that moves the interface. And then we go back up, and with a new interface, we solve a new FE problem. We get new motions of the pad atoms. We put them in the atomistics. That tells the real atoms how to move, and we go around like that. Okay? And so by doing this, we satisfy the correct displacements at the boundary. That part is kind of trivial. The black atoms are the boundary for both problems. So clearly, we have the right displacement. The key is by having the pad, the non-local forces that are intrinsic to the atomistics, these atoms transfer non-local forces onto the atoms on the interior here. And so it's not a continuum traction, it's a non-local traction, and it's automatically covered exactly as long as these atoms are in the right place. And if these atoms are governed by elasticity, small deformations, then they're in exactly the right place, and they convey exactly the right information to the real atoms in the system. Okay? So we have this full problem. We decompose it into three pieces: the dislocation dynamics piece with a specified boundary, and then an atomistic piece with these pad atoms that come from the solution of the finite element, or this total problem over here. These guys talk to those guys. This interface dictates that problem, and the whole thing is solved entirely self-consistently. You can go through all the math of the two pieces, which I won't go through, and there's some nice things that one can do, but I'll skip over that. So I'll show you some idea of how this functions for a simple problem. So here's a crack growth problem. So here I have finite elements, and way down here at the crack tip, there's the crack tip right there, I have atoms. And we're going to load this in K1, mode 1 loading, and we're going to ask, what's K1C? And this material is a slightly fictitious material. You take aluminum and you put it in a hexagonal lattice, and it turns out that that particular material is brittle. So this is actually, it's sort of looks like aluminum, but it's brittle. So this is just going to be Griffith cleavage. And what I expect is that K1C will correspond to the surface energy of this material, because I'm just creating new surface, no dislocation, emission, or anything. Just normal cleavage fracture. But I'm doing it in this coupled system. And so here I have real atoms, and then I have these pads. So the red atom positions are controlled by the finite elements, and the blue atom are the only ones that are really following this law here. The red atoms are following the elasticity of this law, but nothing else. So only this part is really atomistic. And the question is, when the crack grows, does it know that these boundaries are here? If I make an error in the location of the, if I make an error in coupling these two problems, the crack will know, and it will grow at an incorrect K1. And we know exactly what the K1C is because we know exactly the surface energy. So what we do is we study this fracture problem for different sizes of different number of real atoms. We start out with it big, and we make it smaller and smaller and smaller and smaller, and we measure the critical stress intensity for the crack to grow. Okay? And here's what we get. So this is the critical stress intensity as a function of the number of atoms, the number of blue atoms. And here, if you start out with lots of blue atoms, 5,000 or 6,000, just pay attention to, say, the dark red for the moment. The crack will grow at a critical stress intensity, K1C, of about 0.285. Don't worry about the units. And if I make the atomistic region a little smaller, I get the same number. If I make it a lot smaller, from 4,000 something to 1,000 something, I get a slight change. Look at the scale here, 0.28, 0.285. So the change from here to here is about 0.001. And then I make it smaller, nothing changes, smaller, nothing changes. And finally, when I get down to this size, which only has 45 atoms in it, I get a slight increase in the stress intensity. Now the Griffith condition for this is right about 0.285. and or actually right about here. This is to grow the crack forward. This is actually lattice trapping. If I try to grow the crack forward, I load, it moves forward at a certain stress. It starts to close at a slightly lower stress because there's a slight atomistic effect called lattice trapping that gives a little bit of asymmetry. And so this is the Griffith point, but I could come all the way down here. I can use 45 atoms instead of thousands, and I make an error in the Griffith condition by about 3%, 0.29 versus 0.28. And if I use slightly more atoms, I make almost no error at all. The error is fractions of a percent. And so that tells me that this coupling between the atoms and this continuum region is so accurate that there are no energy errors to the scale, certainly here, no energy errors to the scale of very, very small energies that translate into about 3% in the K1C. And of course, the fewer atoms I have, the less expensive the method, because the expensive part of the calculation is associated with how many atoms I have. The finite elements on the outside is essentially elastic, and it's very inexpensive. The other thing that you can find is if the crack starts growing, it will stop if it encounters some sort of spurious forces that decrease the stress intensity. But in fact, these cracks go all the way up until they get to the finite element. And that tells you that they don't really see any spurious force. As soon as they start growing, they just go straight across. And they get to the boundary. They stop at the boundary because now there's no way for the finite elements to come apart. Only the atoms can come apart. But they don't stop somewhere in between. And if you had an error, the crack would either stop or it would accelerate at a lower stress intensity. So the atomistic coupling here, using this decomposing method, is extremely accurate. Now, for the plasticity parts of the problem, we have to worry about the dislocations. And if I have an atomistic dislocation, it corresponds to shearing of atoms. It corresponds to 100% shear strains. But finite elements is a small-scale elasticity problem. It's linear elastic, so I can't possibly shear something by 100%. The stress for that would be the elastic modulus. So the finite elements themselves can't handle an atomistic shear. They handle these discrete dislocations back here because we put them in as automatically as a continuum entity. We don't put them in atomistically. But if I have a dislocation from the atoms coming up toward this boundary, it can't possibly go directly into this material, because this material is this linear elastic material. So there's a problem right here at the boundary, and I need the dislocations to be able to go back and forth. Otherwise, all of this is pretty useless. And here's an example of what happens if you just straight away take this coupled system and load it up with some dislocations. So here's a little void in the middle of this is the atoms and this is the finite element, and the interface is right here. And if you load this up at a certain stress, this void will nucleate dislocations, and they will head off to this interface. So back here is the void. Now here's a dislocation that's come along. It's a little hard to see, but you can see if you look carefully, there's a shear right here. The triangles have changed their orientation. The red line is covering it up. So the dislocation is coming along, and it gets up to this interface. It can't possibly permeate this interface, and what happens is it gets reflected and goes off this way. This is entirely fictitious behavior. And so the interface would have a terrible influence on the plasticity because the plasticity can't escape, and this behavior is completely fictitious. And so I would never want to have this. I have to, as the dislocations are coming up, I have to find an algorithm to get them to go straight across the interface. Can't tolerate this. So the way we do that is to first find the dislocations and then toss them over the fence to the continuum side. And you do that by, here in the atoms, we have the atom positions. And we know that dislocations come along correspond to shearing along this plane or this plane or this plane. And so if I look at this little thing and I think about it as an element, like in finite elements, it's 3 atoms, but I can think about it as an element. If it shears in one of these directions, so that this atom moves to here or this atom moves to here, it has something like 100% strain. I know a dislocation has gone by if this thing gets sheared along one of these planes. So as you run your atomistics, you simply sit here and look at all these blue atoms, all the triangles formed by these blue atoms, and you ask, when do I see a shear that would correspond to a dislocation? These are just offset from the interface, so the dislocation is normally coming along here. Nothing's happening. It's perfectly fine till it gets up to here. And at this point, we look over here and we see that this element has been sheared, and because of the direction of the shear, we can tell exactly what the slip plane is and exactly what the Burger's vector of the dislocation is. So this is the detection of a dislocation in the atomistic system. And here's a little bit more of a picture. If I have an atomistic system like this, and there's a Burger's vector, when the dislocation goes by with the Burger's vector, atom 3 kind of moves over to here. So this triangle, even if there's a rotation, it shifts over. It's rotated, but it's also shifted. This atom used to be 3, 1, 2. Now it's 3, 2, 1. And that's because the dislocation has gone by on this plane. And there's been a rigid rotation just to show that, that kind of thing could happen. But we know exactly how to measure the strain in the element in terms of the normal and the Burger's vector. We know that strain due to a dislocation is exactly this. And so if we see that strain in an element, then we know what the dislocation Burger's vector was and what the slip plane was. So we just sit and measure the strains on all of these elements, and if we get this strain, we say, there's a dislocation there. So that's what's happening when we detect. So a dislocation is coming along here, it's been shearing the crystal, and it gets to this point, and our blue element is being sheared, and we say, it's sheared, there's a dislocation. And we stop, and now we do something we call a passing algorithm. What a passing algorithm does is essentially moves this artificially from this position to that position, but instead of it being atomistic here, it's a continuum entity. So it kind of mysteriously changes its identity from an atomistic dislocation, which corresponds to a range of some sort of deformation of atoms, to a discrete dislocation. And the way we do that is by adding a negative dislocation here and a positive dislocation here. The negative one, because they've got 2 separate slip planes, these 2 annihilate and give me back perfect crystal. And this one is now just the extension of this one, as if it had glided to this position. But this is a continuum dislocation. So now I put the continuum dislocation in, these 2 get annihilated, and this one is now on the continuum side of the calculation. I couldn't allow this to happen naturally because it would come up and bounce off. So I detect it a little distance away, and then we do this little trick of adding a negative and a positive over here, and now this guy is over here. If the equilibrium position of this dislocation wants to be over here, then this makes no difference. I just artificially moved it to here, and then later the stress field will push it over here. So there's actually almost no approximation in this. And the closer I can get to the interface, and the shorter this distance, the smaller and smaller approximation I make in trying to transfer the dislocation. So the error is very computable and very controllable. And if I have, and this is how we get an atomistic dislocation to become a continuum dislocation. We kind of switch its identity. And we do the opposite. If I have this dislocation in the continuum was coming down here, I can just jump it over here and create it as an atomistic dislocation right away. There's no problem. So now we can transfer dislocations back and forth perfectly well. So here's a test of that where we did a 2D problem. We have an indenter with a very sharp tip, and we indent it, and that nucleates dislocations here and sends them into the material. And so they're nucleated. That's an atomistic process. They then come down. They get pushed across the boundary from the atoms to the continuum, and then they come to rest somewhere in the continuum. And we do this problem with our coupled method, and we also do it compared to full atomistics. So the full atomistic solution has about 100,000 atoms. That's easy to do nowadays, but when we did this, that was kind of a lot. And the CAD method has 2,800 atoms here, and then about 539 finite elements. And so we're really limited by our ability to do the atoms, not to do the finite elements. But already this problem is 30 times smaller than the atomistic problem. But we want to be able to do it so we can compare a full exact atomistics to our method. So dislocations are emitted here, they get passed across, and they come to rest. So here's the force versus indenter displacement. The atomistics and the CAD, you load up. At this point, you nucleate a dislocation, you get a force drop. You load up, you nucleate, and load. And you can see that the points of nucleation are very well captured. And the difference between these is because the continuum here is linear elastic, and the atomistics are slightly nonlinear elastic throughout the material. So the mismatch here is because we treated this as linearly elastic, and the forces are quite high. But otherwise, the nucleations are occurring at the right place. And then the position of the dislocations, it's nucleated, and it comes and sits here. And the CAD says it sits here. We're a little bit off, but it's very sensitive to the applied stress. And if you realize that the atoms have a very small chiral stress, that it takes 3 megapascals to move the atoms, then if you add that in the simulation, you find that the dislocation position matches up. And back over here, that dislocation came out and sat right here. When the second dislocation nucleates, it pushes the first dislocation closer to the boundary. When the third one nucleates, it pushes the second and the third one closer to the boundary, and these are the final solutions. So fully atomistic is the black, and where the dislocations are here. The white ones are the approximate coupled method. So we have the non-continuum phenomena of nucleation here, but then we have the plasticity in the far field is captured accurately by the discrete dislocations, and the dislocations can pass across this interface without any problem. So we have this method, and let's look at a problem that maybe is relevant to fracture. And this has to do with crack tips in FCC materials. So one of the things that is important, particularly in metals, is emitting dislocations from the crack tip, because this is a method to blunt the crack and make it harder to cleave. So it's important, if a crack tip does not emit dislocations, the material is brittle. If it does emit dislocations, then it blunts, and you can activate far field plasticity mechanisms. So what happens at the crack tip is very important. And in FCC, dislocations, if you have a normal dislocation, it splits into two parts with a little stacking fault in between. And so when you look at a crack tip in an FCC material, you load up the crack, and it emits the first half of the dislocation. Where there's been one plane, there's supposed to be two in aluminum, and leaves behind a stacking fault. And then this dislocation moves a certain distance away, but it doesn't move very far away. And then if you keep loading up further, the question is what happens? And there are two things that can happen. One is that the second part of the dislocation can be nucleated on the same plane, and then this forms the full dislocation, and then this thing can move away off to infinity. The other thing that can happen is at the crack tip, you can nucleate another partial dislocation that's the same as the first one, but it's shifted by one lattice plane. And this is the beginning of a twin. A twin is a stack of these kinds of partial dislocations that exist in the material. And so you have two possible options. One is full dislocation emission, and then the crack tip is regained, but it's slightly more blunt than it was here. The other one is you form a twin, and the dislocations never escape the crack tip, and they influence what goes on at the crack tip subsequently. And if you have twinning, you can get relatively brittle behavior, and if you have full dislocation emission, then the crack tip just keeps blunting. Now this is the simplest deformation problem in metals, but no one actually could predict when you get this and when you get this. Okay? And there's, in the recent literature, a lot of discussion about, well, in what materials do you get this and what materials do you get this? And that has an impact on fracture. Now, experimentally in aluminum, you nucleate partial dislocation and then you nucleate a full dislocation, and really what you see is this, and the full dislocation goes far away. And you almost never observe twins at the crack tip in aluminum. If you do molecular dynamics and you do theory, you always predict twinning. If you take a continuum theory for dislocation emission, it predicts you should get twinning. If you do molecular statics, that is molecular dynamics at 0 temperature, you get twinning. That is, you don't emit this extra partial, you emit this pair, and then another one, and it forms this twin. And if you do molecular dynamics at finite temperature, you also get this twin. So if you look more broadly, some FCC materials, like iridium and silver, they twin at room temperature and low loading rates. Aluminum and copper twin at low temperature or high loading rates. Aluminum and platinum typically not observed to twin. But in fact, in molecular dynamics, all of these twin. Okay, so you do molecular dynamics, and you predict that they all should behave the same, and experimentally they don't.
And aluminum and magnesium twin?
I don't know.
Yes.
Okay, I haven't looked at that. We'll have to put it in, nanocrystals, yeah. So nanocrystals are a little different in some ways because the stress fields, nanocrystal and aluminum will also twin. And you can find twinning at the crack tip in aluminum. You have to look very hard, it doesn't happen all the time. But by and large, these are the trends. But you go to nanocrystals, then you have much higher stresses and grain boundaries and other things. So generally, this is the phenomenon. So what's going on here? Why doesn't molecular dynamics give us the right answer? Why does it not distinguish between aluminum and silver, which are very, very different? And the resolution between theory and experiment is that these phenomena are rate dependent, thermally activated nucleation. And in molecular dynamics, you don't get that. That is, you're doing things too quickly to observe the correct behavior. So to demonstrate this, here's what we did. We took our multiscale method, and we put, here's the finite elements, and here's the crack tip. You've seen this picture a number of times before. The crack is actually not, there's a plane strain loading, but the crack actually has a three-dimensional length to it. I'm not showing you that. And when it nucleates a partial dislocation, that comes out as a little loop. This is a picture from some other work. But you nucleate a loop, and then the loop expands, and then it goes off as a dislocation. And so we take this material, we do exactly what's full anisotropic mode 1 stress intensity field at infinity. We have this sharp crack. We load it to a certain K value, and then we just fix the load, and we hold it there, and we wait. Now, in molecular dynamics, wait means the computer chunks away, 1 femtosecond time step, 1 femtosecond time step. And you have to have all the atoms moving. And in this problem, because this partial dislocation comes out, you have to keep that in the problem because this dislocation influences what goes on at the crack tip, and it plays a role in what happens next. But unfortunately, when it comes out from the crack tip, it ends up way over here somewhere, like down there. And if I needed to keep all the atoms in the problem to keep that dislocation in the right place, computationally, I can't do that number of atoms. In our method, the dislocation comes down, it gets passed as a continuum, and it sits in exactly the right place down here somewhere, but we don't have to have an atom description of it. It gives the right fields back to the tip, and all we need atomistically is to keep the tip. Right? So even in this very simple problem, because this dislocation has to sit out here somewhere, having the multiscale method is essential. So we load the system up, the first dislocation comes out and it sits here, the first piece, and then we just wait. Now, you have to do a lot of simulation. It turns out that you can do it in certain special parallel ways to accumulate a lot of simulation time. But I'll just show you the result. So here are the two possible outcomes. One of them is the second dislocation makes a full dislocation and this moves on its merry way. The other one is that this forms a beginning of a twin and you get twinning. The symbols here show what happened. We fixed the K1 value, and at this time, so many picoseconds, something happened. And the orange color are twins, and the black color are partial dislocations. And if you look at molecular dynamics simulations, they're almost always down in this regime here, 100 picoseconds or less, and as a consequence, they're always at high loads. And so typically in molecular dynamics, you're down here, and this is why all the reports in the literature give that you see twinning, because molecular dynamics is small timescales and high loads, and at small timescales and high loads, twinning is actually preferred. But experiments are not done on 10 picosecond loading times. They're done on 1 second loading times. And in our simulations, these are direct simulations. If you wait long enough, in this case only 100 picoseconds, but there's 2 data points here and 1 here. If you wait more than about 10 nanoseconds, the dislocations are trailing partial dislocations and you get this picture. So the molecular dynamics simulations that everyone has looked at in the literature were all down here, and they could never figure out why you would get this behavior, because they couldn't go to long times, and they couldn't go to long times because they have to capture this dislocation way out here, which means it's too big of a system, which means they couldn't do the molecular dynamics long enough. Plus, they didn't think of it, but that's a separate issue. Even if they had thought of it, they couldn't have done it. And so here we directly see the transition between twinning, and then there's a region where it's kind of mixed, and then it transitions to being the trailing partial. And that is the full dislocation. And experimentally is up here, right? Long times, on a scale of picoseconds. This is a microsecond, right? And experiments are, say, up here somewhere, maybe even up here. And so the MD is just looking at the wrong thing because of time scales and length scales. And using the multiscale, we can reveal the real behavior. Now, oh yeah, we did a calculation that it would take 2,000 CPU years to have gotten that data point in normal MD because of the size of the system that would have been required. Now, as I mentioned at the break, we want to understand this behavior more fundamentally. And this is where theory comes in. So we see this behavior. You say, well, why does it occur? Why does this occur if I have low stress and long time and this occurs in this regime? What's happening? So here we go back to theory. And so this is Rice developed a model for dislocation emission at crack tips, and Rice and the student Glenn Beltz modified it further. And the idea is you have a crack and you emit a dislocation, but there's a barrier to emitting the dislocation, and there's an energy, and depending on the path that you follow requires different energies. And there's an energy barrier for these two processes, whether it's the twinning or the other one. And if you have an energy barrier and it depends on stress, then you can switch from one barrier to the other as you change the stress or change the temperature or change the time. And so I don't want to go into detail about this, but you can think that I have a state with no dislocation and a state with the dislocation, which is lower energy, but there's a barrier I have to overcome by thermal activation. And there are two processes, and each one has a barrier, and that barrier depends on stress, and I'm going to see the one with the lower barrier because that's going to occur faster at any finite temperature. So it turns out, after some effort, you can actually calculate this in the Rice model and using the material parameters, and here's what you get essentially for the predicted time as a function of the stress intensity. This is what you get for partial dislocation emission. This is what you get for full dislocation emission. And so if you're at short times, you get this behavior because it's at lower stress. You don't get to this because this happens before. You're loading up the system, or you're holding it at this stress and waiting, and holding it at this stress and waiting. And this takes too long, the barrier's too high. But if you lower the stress, it turns out the slope of this line is lower than the slope of this line, and you predict a crossover. So up here, you'll now see this process because it occurs faster than this process. And so analytically, by doing the right fracture mechanics with the atomistic details, but in a continuum model, we can predict that this transition exists. Okay? And it's not in perfect agreement with the simulations that we predict the transition here. Maybe the simulations say the transition is somewhere here. But it's an analytic model, and it shows exactly the phenomenon that's appeared in the simulation. And now this is where I come back that the nice thing about the analytic model is it can now be extended to other materials. And it turns out that in this model are all kinds of things like stacking fault energies, all kinds of material properties that we can measure. And so if we measure these material properties, put them in the theory, we find that the activation energy versus stress will find a crossover that that the purple, if the orange is to the left, it means it's favorable. If the black is to the left, then it means it's favorable. So this is twinning and this is not twinning. So at all of these cases at 0 temperature MD, when the activation barrier is near 0 at low temperature, predict twinning occurs before partials. Twinning, partial, twinning, partial. But they all have this crossover. And the crossover occurs at some typical barrier value. In aluminum, it occurs at a low barrier. At iridium, it occurs at a huge barrier that's off scale. And from that, you can then calculate, well, how long does it take for that transition to occur? That is, how long would you have to wait to see this behavior? And you find that in aluminum and platinum, you only have to wait microseconds. Gold, a little bit more, but still microseconds. Iridium, gigayears. And so experimentally, we see twinning in these materials. We don't see twinning in these materials. And we see twinning in these materials at low temperatures or low temperatures or high strain rates. And so this prediction, which came from the model, which came from the multiscale structure, multiscale study, actually provides the right description of which materials twin and which materials don't twin at the crack tip. Okay. So this is not the final answer for fracture of aluminum or fracture of platinum. There are all these other higher scales. But fundamentally, what goes on at the crack tip, nobody knew. Whatever we could get out of simulation was giving us the wrong behavior. It didn't agree with experiments. And the use of a multiscale model of this type allows us to access time scales and stress scales that reach to the experimental trend toward the experimental scales, allow us to see the correct thermal activated behavior and explain why the experiments are the way they are. Again, there's a lot of other stuff that goes on farther away, but that's not in this study. Okay. So I argued before that the multiscale models needed for fracture. What I told you about is a little bit of detail of how, just to give you an idea about coupling methods and what kind of things one has to think about. It's not only mechanics of stress and displacement that have to be continuous, but it's also transferring of defects across the interface. And in this case, we talked about atomistics and continuum dislocation dynamics. And then I showed you sort of a few proof of principle examples and a preliminary application of, to the twinning problem, which really revealed something new about what goes on at the crack tip. And we're now trying to use this to understand a lot of other problems. Embrittlement, I showed you a little bit about the iron hydrogen. These issues of dislocation, emission, and cleavage at the crack tip, and how they interplay against one another, and how that depends, again, on things like alloy. And the reason you said aluminum magnesium, so when you put the magnesium in, you change some of these energies. So I want to go back and put it in the theory and see what happens. Maybe we get...
Magnesium segregates around the grain boundary.
Oh, okay, so it's along the grain boundary. But we can start to understand these as sort of material science problems associated with fracture at a mechanics scale. We can do things, as a matter of fact, like grain boundaries, right? That a grain boundary is a hard thing to do in a continuum model because it's just, okay, there's some interface and it has some energy associated with it. But in fact, a grain boundary has a lot of structure and it blocks dislocations, and the structure leads to different things happening at the crack tip, and cracks come to the grain boundary. What happens? This is all intrinsically atomistic phenomena. And the continuum just says it's a boundary. It's a perfect boundary with some basic property, and we're not quite sure what it is. So these kind of problems, we can put a grain boundary along here, we could put a grain boundary here, we can put the atomistic detail into the problem and extract out what goes on at that small scale, and then try to couple that with what goes on at the larger scale. Okay, so that's all I have to say, and I think we'll skip the dislocation dynamics, which you have the notes for. Doing these multiscale things requires learning new concepts, learning a little more physics, a little more material science, this molecular dynamics, this dislocation dynamics, quantum mechanics. And so it's not the kind of thing everybody can jump right into, but my experience is that people who've been doing applied mechanics, like all of you, are very good at math, and a lot of you are already doing numerical computations of problems with singularities and other things. And so these other methods are very accessible with a small amount, moderate amount of study. Molecular dynamics is particle dynamics, F equals ma. You did that when you were a first or second year student. It's a slightly more complicated, but that's all it is. Quantum mechanics, it's a little more subtle, but if you know what you want to get out, then you can learn enough. Dislocations, this is applied mechanics, and dislocation theory is elasticity. So in fact, while you can't rush into these things, it is not, there's not a huge barrier to getting into them. You can't, you have to make some commitment to do it, and you have to identify sets of problems that you want to work at. But it's not insurmountable, particularly for a group of researchers with your kind of background. But you have to do it in a serious way, meaning it's not something where you download the codes and just start doing a calculation because it seems like a good idea. But everybody can really understand all the fundamentals and learn reasonably quickly. And this is the way a lot of applied mechanics is going, where students are learning quantum mechanics, molecular dynamics, discrete methods, mesoscopic methods. So I think we'll see more of it as you go along in your career. It could be helpful for some of the research you do in the near term. It's not for everybody, and we're not going to connect the pipelines tomorrow. But what's that? But there are physical phenomena that are important to understand that are just below the scale that, as mechanics, fracture mechanics people, we're not used to dealing with, and we have to pay attention to them, particularly now as we try to optimize and design new materials. So with that, I'll quit. I won't give the number 4, and you can look at it in your notes. And then I think the reception starts at 5:30, so we'll be the first ones there. All right, thanks. And I'll take questions if anybody has one or two, or we can. And you can also walk out if you're thoroughly satisfied. Yeah.
We saw here that during the propagation of the crack, the material doesn't break
fractures, but within the materials proximity of the fractures. Is it possible with this method to predict this phenomenon?
That's very difficult. These things are often caused by heterogeneity, right? That things are not perfect, so there's more segregation over here, or this boundary is a little different than this boundary. It's also difficult to understand because the stresses at the crack tip should be very high, and the stresses a little further away should be rather lower. And nucleating cracks is difficult. So I'd say nucleation of microcracks, if it really is a separate crack, is still a challenging topic. There's no question that you see it experimentally, there's no question it occurs, but to understand what really drives it at the microscopic scale, I think is still fairly open. I don't know, you might agree or disagree.
No, I do agree with you. The material that you are modeling is not the material that I showed yesterday. In the aluminum alloy, I showed that using tomography, X-ray tomography, it's clear that the crack is not propagating from the crack tip. And the reason for that is because we have some impurities, some inclusions. And because of the mechanics, which tell us that for a blunted notch, the maximum stress is not at the crack tip, but within the material. This can explain.
So in your cases, you have this large crack, which is fairly blunted, and then I would say that the small crack that's propagating back.
Not a long crack, you know. It's on tomography we do not have.
Okay.
Just perfect. And as for cleavage, it's also extremely well established. If you look at the textbook by John Knott, there is some beautiful pictures showing that the cleavage cracks, you have the main crack, and the cleavage cracks are initiated within the material. If you look at the reverse, for instance. So the reason for that is the same, because we have some inhomogeneities. Material that you are modeling have no grain boundaries. Grain boundaries are very important for fracture because we have to. It's an interesting problem. I will talk about this on Thursday. Crossing grain boundaries by cracks.
There's a little bit of work. People are doing atomistic things, but it's still limited. The other thing is when you have these little cracks that the small cracks that nucleate in front of the big cracks, well, those have crack tips too, and they're growing for some reason. So we have to address why they nucleate and why they grow. And the growing of those is sort of similar to this once they've been nucleated, but the blunted one is not so. So I mean, we still have to ask the question of any crack it forms, unless we try to cut a notch in, and then why does it grow? But we're still away from dealing with all the complications in real materials. We keep working at it, but okay. Any other question? You had a announcement or a?
Yes, he has an announcement for you.
Oh. Oh, my pleasure. Thanks very much. Ah, wonderful. Norwegian Scandinavian style is wonderful. Thank you very much.
After 24 hours intensive teaching and learning, I hope you are very prepared for conference. I hope now you have a nice view of the fundamentals of flux mechanics, computational flux mechanics, advanced application, passions, and most important, the future.
Always the future.
Yes, the school is closed. Let's thank the 4 teachers again.